Recall that this is the general setup for a first-order differential equation. You've got something that is either written like this, or you can rewrite it to have this form. Derivative of x equals, and then some prescription for the derivative of x in terms of x and in terms of t. So for example, like x prime equals rx for a population model, maybe plus some other stuff involving x and t and whatever. This is the kind of thing that a first-order differential equation is. And they're usually pretty hard to solve, actually, right? Like, if you just come up with a random first-order differential equation, probably you will not be able to solve it. The ones that you can solve because they're textbook problems. They're there because you just learned about one particular solution technique, and then we're giving you one textbook problem to try the technique on. But if when you were picking a topic for your project, if you tried to just randomly invent some models and write down differential equations, you probably saw that it's pretty hard to just invent something that you can actually handle. So one approach to address this is to try to develop more and more techniques, but even all the techniques that are available will not just handle everything. Most differential equations you just simply cannot solve by writing solutions in terms of elementary functions. Another approach is what's called numerical approximation. So that will be the topic of this lecture. Which means what it refers to is not actually solving a differential equation, but taking a particular initial value problem, a particular setup, where you have a number, x naught, for the initial condition for x, and then using the information in the differential equation to make approximate predictions over small time steps, and accumulating your approximate predictions in order to create an overall prediction. So this is what's meant by the numerical analysis portion of your project. Basically, you will do the sort of thing that I'll describe in this lecture. So here is the idea. Suppose you have an initial value problem like this, x prime equals, and then some stuff involving x and t, and you have an initial condition, x of 0 equals x naught. What you want is a solution. So you want x of t. As usual, that's what we want, right? And you don't want a general solution, actually. If I just gave you this, then you would want a general solution so that you can handle any possible initial condition. But if you start with an initial value problem, then you don't really want a general solution. You want the unique particular solution to this differential equation. Let's think about the x of t that we want in terms of its graph, in terms of the plot of x of t. The initial information already lets us plot at least one point. It tells us that, so let's say x naught is this high. It tells us that at time 0, the graph should pass through x naught. So let me make the graph be in green. So it tells us that this green dot here is a point on the graph. So I don't know what else it does, this, but I know it passes through here, whatever is going on. Okay, there's more information contained in here. Also, we know about the derivative of x, because anytime you know what is the value of x and what is the value of t, the differential equation tells you what is the derivative of x. That's what it is, right? That's what a differential equation is that relationship between derivative and those other things. So if I plug in, if I just take this right-hand side expression and I put in x naught for x and I put in 0 for t, then that will tell me what is dx dt specifically when t is 0. So that's telling me what should the slope here be. So let me do slopes in red. So that's telling me, maybe this comes out to be like 1 or something. Then that's telling me that whatever the graph of the solution is, it should have slope 1 as it goes through here. Hopefully this is reminding you a little bit of slope fields. Basically, the differential equation contains this slope information at every point in the xt plane. So here is the value of the slope field, this slope at this point. Now, that does not tell me what the solution graph is, again, but it tells me that it has to be tangent to this curve. So it could do any number of things from here, but it couldn't do like this, right? Because that would have the wrong slope there. So that's pretty cool. Of course, it could make a sharp turn, like it could start like this and then immediately make a very sharp turn and do something that I'm not actually expecting it to do. So that's a possible behavior. But still, knowing the slope does limit a little bit what the function could do from here, what the solution could do from here. So to have the best chance of having the best approximation, I should make a tiny step forward in time from t equals 0 over to, let's say, t equals 0.01 or something like that. So let's make a tiny step forward in time. So for the sake of, so it should be really tiny, right? Like really close here. But for the sake of making the picture look reasonable so that you can see the picture, let me actually make it look big. So pretend we're like super zoomed in on the t-axis. So let's say this is the next time that I consider. But actually, here's time 0, and here's time t equals, I don't know why this is in green. Here's time 0, and then here's time t equals 0.001 or something very small like that. So this is a very zoomed in t-axis. Then I can pretend that it's just going to follow this line, right? So I can sort of use the differential equation as a linear approximation, pretend the function graph is going to follow this line. So just pretend it does that. Then my prediction, my approximation, is that x of 0.001 is here. So that's my prediction that goes just a tiny bit into the future. Since it's just a tiny bit into the future, I don't expect it to be too far off. But at this new location, I can now get a new value for the derivative. So now I can, so let's call this height here. Let me make some space here. Pull the whole picture down. So let's call this height here x1. So this is like the value of x after one mini time step. Then we can evaluate. I don't know why I wrote this in green. This should really be in red since I'm computing the slope. I could evaluate f at x1 and then put in the new time, 0.001. And then that would give me, according to the differential equation, that gives me the derivative of x with respect to t at time 0.001, right? Of course, it might not be perfect because x1 might not be exactly what x of time this time is, right? But it is an approximation. It's good as long as this function doesn't change too quickly when you make small errors in the input here. So maybe when I evaluate here, I get this slope, like that. So the slope here was 1, maybe this was 1, and then here I get something less than 1, like a half or something. Then I can make another little time step, go to t equals 0.002, and extrapolate linearly from there, like that. And if I continued the linear extrapolation forever, I would be seeing this stuff. Or if I continued that one, I'd be seeing this stuff. But I keep sort of correcting course. So I keep doing this, linearly extrapolate a little bit, and then do a course correction using the slope given by the differential equation. Then linear extrapolate a little bit more, then do a course correction again. So again, I look at the value of the slope field here. Maybe it's a negative slope. And then it says, okay, now you need to go down this way. that's at 0, 0, 3, something like that. And you know, if the true function behavior really does something more like, say, this, I don't know, like it starts out here with the prescribed slope, but it changes faster than we thought. So maybe it goes and does something else. Then our approximation is quite bad, right? This looks like a bad approximation. But if remember, this time axis is zoomed in very, very close. As long as we've zoomed in close enough to straighten out the jittery, erratic behavior of the solution, as long as we have zoomed in close enough, this will actually probably be pretty close to the solution. As you can imagine, as we continue this step, we accumulate more and more error. So like here, the prediction is perfect, right? Because it's the initial condition. But here we might be a little bit off, right? And then we're using that information at this location to come up with a new derivative, which could also itself be off because this location might be off. So that's two reasons for this point to be a little bit off. It could be a little bit off because it linearly extrapolated from a point that was, because it linearly extrapolated, it could be a little bit off just due to the error in the extrapolation. And it could also be off because the previous point was a little bit off, and so the slope back here also was a little bit off. So error will accumulate as you go on. So two principles to keep in mind. Error accumulates for the longer time steps you run. The further down, after 100 time steps, there will be a lot more error. You can trust your predictions a lot less than after just 10 time steps. And the second thing to pay attention to is smaller time steps will lead to less error, typically. Okay, so your goal in the numerical analysis portion of your project will be to write code, or maybe it's not code, you'll see I'll give some alternatives, for carrying out this kind of algorithm to work with whatever differential equation you have got. Now, what I've done here is kind of just pictures and waving the cursor around and pointing at things. I'll give you more of a solid description of the algorithm in the next video. Unless you already get it, then you can probably just go ahead and do it with whatever programming language or whatever you prefer. After that video, I will probably just give you some I'll show you explicit ways to do it using certain tools. And by the way, I forgot to mention that this is called, these are called Euler steps, these steps here. So this is sometimes called an Euler approximation. Sorry, I just looked it up. It's called the Euler method. This numerical method is called the Euler method. And it's like one of the most primitive first things you might come up with. And by the way, if you're worried about your differential equation being second order rather than first order, we can apply the same idea, basically. And I'll give you one video showing you how to do that. So it'll just be a little bit more involved. Instead of just determining the derivative, you will also have to use information about the second derivative. Or rather, you can view, for a second order differential equation, you can view it as being a prescription for the second derivative in terms of the first derivative and x itself. Then while you take steps in x0 to x1 to x2 and so on, you also would take steps in x prime. Okay, so I'll show you in an example. Okay, and before I end this video, I really should put this at the end of the lecture, but I'm going to put it at the end of the first video because I know that way more people watch the first video than the last video. So here are some expectations for the numerical part of the project. you are going to apply the Euler method, which is the method I just described here, but that I'm going to describe in more detail in the next video. So to apply that, you will have to fix some initial conditions and fix some parameters in your differential equation. So like if you've got a parameter like h in Newton's law of cooling or something, you'll have to choose a value for that in order to use this method. In the end, the method only works when you have actual numbers here rather than expressions involving some unknown parameters. When you apply the Euler method, this is something you're doing yourself. So do not use some differential equation solver tool, even if it has the ability to apply specifically the Euler method. No, write the code for doing it yourself, and you'll include the code in your project. Let's see, and for different kinds of code, I'll describe what I mean by include code when you see the videos about the code, which are coming pretty soon. Generate some nice plots. So that's part of the whole point of doing this, is that you will be able to generate plots with it, even without solving, right? This idea allows you to generate plots of approximate solutions without actually having a solution. So at the end, we'll have this nice green plot, but we did this without ever having x of t equals and then some expression, you know? So it'll be really nice to have some plots for that. And I say plots and not plot because every different initial condition choice is going to give you a different plot. Every choice of your parameters in your differential equation is also going to give you different plots. So you can explore as you vary different parameters what different things can you get. So these are kind of the talking parts of it. So you've got your code, you've got your plots, and then the talking. Two things to pay attention to mainly. Compare what you got with what your expectations were from your theoretical analysis. So you already had some ideas in your theoretical analysis. Were you surprised by anything that came up in the numerical portion? Did it correct any previous thoughts you had? And finally, did it give you any new insights that you did not previously have with just the theoretical analysis? For example, if your differential equation was so complicated that you could not even solve it in your theoretical analysis, then definitely there are going to be some new insights when you look at your numerical solution, because that will be your first time seeing a solution in the first place.